Okay, so let's explore a new topic. So look at this picture right here. I kind of call it the envelope. And you might have seen some of these before. They're pretty popular problems going around the internet. But can you draw this shape if you start somewhere and you don't lift your pencil from the paper? Okay, so just go ahead and take a second, see if you could do it. And you can always just draw like 1, 2, 3, 4, 5 dots. One like this. And then you practice, okay? So go ahead and pause and see if you can. Okay, well, after an attempt, you have some choices. So I started right here and I just went around, okay? So we're going to explore how to do problems like this or if they're even possible. Okay, so you should be able to tell just by looking at a shape if you're able to do this or not. Okay, now doing it is another skill, but knowing whether or not it's possible, that's just math. Okay, so there's actually going to be many situations in real life that apply to this same idea. It's not just always drawing things and stuff like that. So remember, these are all networks. And so it's about traveling from place to place, talking to people in groups, things like that. So lots of different applications. So we're going to explore one of them. All right, way back in the 1700s, there was a person who lived in Königsberg, and he wrote to Leonard Euler saying that a popular pastime was for couples who lived in this city. There were 7 bridges, and they wanted to cross each bridge exactly one time, okay? And so what he wanted to know is he asked Leonard Euler, is this possible? So here's a picture of the town. And then these are the 7 bridges, okay? So you kind of want to think like, okay, if I was here and I traveled across bridge A, and then I went to bridge C, and then we went to bridge D, and then so on. Is there a way that I can go to all 7 bridges without backtracking? Because I only want to do them once, okay? And I don't have to end up at the same spot. That's not a rule, okay? So if you Google this, there's lots of videos on it. It's kind of how graph theory got started, to be honest. So you take a second and think, what do you think? So let's see. I'll just keep going. Let's say I go to B, and then I go to F, and then I got 2 choices. I can go to G or E, but no matter which one I pick on my route, if I go to E or G, I can't get to E now. So if I pick this path, I'm obviously not able to do it. But they don't tell you where they're starting. So then you kind of want to say, well, what if I started in the middle, and then pick out. Let's see, I went here. Then let's go to A. Then let's see if we can go to F. And then I do E and then B. But then how do I get to G? Okay. So then maybe I start, you know what I mean. Okay. Let's erase that. And maybe I start here. Okay. So there's lots of different options, but is it possible? He said, hey, Mr. Euler, and that's how we pronounce it, Euler, not, or Euler, sorry, Euler. So what happens is Euler said, hey, you know what? I could just draw these as nodes, and these could be my edges. And this really is kind of like a network. So Euler said, you know what? This is kind of what I do with networks. And this idea gave Euler the idea for graph theory. So 2 terms. If we have an Euler path, a path is we're just going to keep continuing, and it goes through every edge once and only once. And that's the bridge idea, okay? So when we had those bridges, we didn't want to cross one bridge more than one time. That's a path. Now, sometimes we've been using paths where we could go back and forth, but that's not an Euler path. That's just a path, okay? An Euler circuit, so I think of circuit as circle. So you have to start and stop at the same spot. So like if I was at A, I could go all the way around to different places and then I end, okay? So think of a circuit as a circle. You end back where you start. Notice it doesn't say that you can only do them once, okay? So these are some examples if we take just these two different shapes, and I had to pick different shapes for these. So if we have an Euler path, notice I can start at D, and then we can go D, E, B, to C, to A, to B, to D, to C, to E. And so that first task, this is one of your options. It really is a path problem, okay? An Euler circuit, we had to start at D and we had to end at D. Well, that's not actually possible on that first drawing, but it is possible if I add to the shape. So now we could do that same idea, and notice the paths are the same, except then we get, once these are all covered, then we can end at F and then D. So I could end where I started, okay? And so that's a circuit. We started and ended at the same spot, okay? So how do we figure out which ones have paths and which ones have circuits? That's what the goal of this video and notes is, okay? So if you have a connected graph, which means all the vertices are connected, there's not like this is unconnected. I'll show you. Like if we had A, and then let's do this, B, C, D, E. See, A is not connected to all the other vertices. So remember, connected means that they are all joined. There's not one just off by itself. So if you have a connected graph, you want to count the odd vertices. So like right here, B, this has 1, 2, so B has a vertex of 2 degree. A, this is 2 degree. E has 1, 2, 3, 4. C, 1, 2, and D has 1, 2. So these are all even degrees. Look at A. Here's 2. B has 1, 2. C has 1, 2. E has 1, 2, and D has 1, 2, 3, 4. So if we have all even vertices, that means there's going to be a path, okay? At least one path. They don't tell you where you are, but we can have a path. Now, an Euler path is also an Euler circuit. So all even degrees means you also have a circuit and path. All right, so somehow I could start like at A and I would be able to go all the way around and end back up at A. So remember that. If they're all even, you have both a circuit and a path. Next, oops, I'm going to make this smaller. I don't want to make it smaller. Let's move this over. There we go. The next says if we have 2 odd vertices, and it has to be exactly 2, okay? Then we can have a path where we can start somewhere and end and hit all the edges, but I can't end and start at the same spot. So if I have 2 odd, then I can have a path. No circuit. So like here, A has 2, D has 1, 2, 3, B has 1, 2, 3, 4, C has 1, 2, and E has 1, 2, 3. So because E and D are odd, and I have 2 of them, I would have a path. Now, the rule is, this helps you. If you have a path, you have to start at one of the odd vertices. So I could start at D, or I could start at E. And the way it's going to work is if I start at D, then I end at E. If I start at E, I have to end at D. So let's try it. So let's start at D. So I'm going to just do, here's that. And I could go on each edge one time. There, 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 and I ended at E. Okay, so you can hit the letters more than once, but you don't go over the sides, which are those bridges, more than one time. This one has a lot of vertices, but we're looking for the odds. So we've got 4, 1, 2, 3, 4, 1, 2, 1, 2, 3, 4, 5, 6, 7, 1, 2, 1, 2, 3, 4, H, 1, 2, 3, oops, sorry, 1, 2, 3, 4, I missed that bottom, G, 1, 2, 3, 4, I has 1, 2, 3, 4, 5, and J has 1, 2, 3, 4. So I've got I is odd and E are odd. So since there's 2 of them, we would have a path, and I could start at E or I. Okay, I'm not going to go through that one, but you can. Pause it. All right, the last rule, so there's only 3, is if a graph has more than 2 odd vertices, there's no path and there's no circuit. So 4, that has 1. This one has 1, 2, 3. 0, sorry, 1, 2, 3. 2 has 1, 2, and 1 has 1, 2, 3. And so we have more than 2 odds. So this is no path and no circuit. So you could spend forever trying, but if we have these rules, and Euler came up with this, he discovered it. Remember, there's no internet or video games back then, so he just took time after time after time, and after you do so many, you can generalize a rule, and that's what he came up with, okay? So as a reminder, if you have all evens, you get a path and a circuit. So all evens, you get path and circuit. If you have 2 odd degrees exactly, you have a path. And if you don't have either of those, you have no path and no circuit. So really you can memorize 2 rules, because if these 2 rules don't apply, then you get nothing. All right. So Fleury came up with a strategy to help you. So he said, and this is for circuits. So he's saying if you don't have any vertices, you could start anywhere. It really does not matter. Okay. If you do have the 2 odd vertices, you do have to pick them. So you want to eliminate them. And if you have a choice between a bridge and a not bridge, the remaining, always choose the not bridge. Because remember, you can't go back and use an edge you've already used. All right. So I like thinking of the edges as bridges. Don't cross the bridge. So what we want to do is I'm going to give you a few questions on your quiz, just like this. So I'm going to give you a picture and I say, hey, I don't need you to draw it for me, but is it possible to have a circuit? So remember, if we want a circuit, what we need is all even degrees. Okay, so what are you looking for in mind? So then we just start counting. So 1, 2, 3, 4, that's even. That's 2, so that's even. F, 1, 2, 3, 4. D has 1, 2. And notice how I said 2 and then I wrote 4. I marked them because it's how many are touching that vertex. B has 1, 2. C has 1, 2, 3, 4. And E has 1, 2. So I would say yes, they were all even. So I would be able to start at any letter I wanted to, and we could end up back at the same spot. That's what Fleury decided. Euler said, if it's possible, and then Fleury came along and he gave you a strategy. And he said, no, it doesn't matter. All right, let's try this one. So now for question number 2, this is the same shape. We just said that we do have a circuit. So now I'm going to tell you to start at B, and I just want you to write your circuit, okay? So if we start at B, I'm just gonna pick A next. Then let's go to G, and there's more than one right answer, so that's why you're just writing them out. Then we're gonna go to F. I don't know. Let's go back to A. It really won't matter. Then we have to do D, because see, I can't go over another purple path if I've already done it. Then I can only go to C. And I could go to B, but then I wouldn't have hit all the edges, so that wouldn't be a circuit. So let's go to F. Let's go to E. Then C, and you can always just draw this on your own piece of paper, okay? And then I can go back to B. So if you typed that into your quiz, that would be full credit. All right, my next question, it said, consider this network below. Does the network have a Euler trail? Now, trail is another word for path, okay? So remember, we can have a path if they are all even, or if we have 2 odd, okay? We can have a circuit if they're all even. So let's go ahead and find their degrees. So here's 2, 1, 2, 3. C is 1, 2, 3. D is 1, 2, 3, 4. And E is 1, 2. F is 1, 2. All right, so even, 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 even. I don't even count evens. We've got 2 odds. So that definitely means I have a path, but I don't have a circuit. So which one does that say? It has a circuit. Nope. Path, but not a circuit, and not a path. So that one's it. So think of a trail as a path, like you're hiking. All right. So if we use Fleury's algorithm, which means don't cross any more bridges more than once, and which vertex can the trail start at? So remember, these were our odds, so we can use either one. So you have to start. So must start at the odd vertex, and then you end up at the other one. So I could start at C or B. And I'm going to say select all, okay, on your quiz. So that's the idea. It's pretty straightforward. Sometimes this will be easy for people, but you just want to memorize those rules. You have a path if they're all even degree or 2 odd degrees. And you only have a circuit if they're all evens.